Hello everyone, welcome to Prakriya Educations. I am Mallikarjuna. In this module, we shall solve a lot of problems on types of relations. Check whether the relation R defined in the set Z given by the relation R is reflexive, symmetric and transitive. Now, they have given you the set of integers. You contain all the negative numbers, 0 and positive numbers. Since the set Z is an infinite set, if you are converting the relation R into the roster form, even that will be an infinite set, and hence we prefer to prove this problem in a general way. Now, starting with the first one, that is the reflexive relation. Remember the condition of reflexive relation, you need to prove A, every A belongs to the relation R. For all this element A belongs to the set A. Here the set A is nothing but Z. Now we shall consider an element X from the set Z, an integer. I am just selecting an integer, a random integer from the set Z. Now, in order to prove that it is a reflexive one, I need to take this element twice because A, that is X, X you need to prove. Now, according to the condition, they have given the condition that if you are making the difference between any two integers, then the resultant number is also an integer. Now, if I am taking the same element X twice, if I am taking X minus X, the difference between this gives me 0, and you know that 0 is also an element from the set Z, right? And hence you can prove that this condition, the condition of the relation is satisfying. If you are making the difference between the same element, then I am getting a number which is in the set Z, and hence you can prove that it is an integer, and hence X, X is an element in the relation R, and therefore you can conclude R is reflexive relation. The second one, that is symmetric relation. Remember the condition of symmetric. If an element of kind A, B belongs to the relation R, then the reverse order pair B, A should be also in the relation R. Now, let us consider for the symmetric relation you need two elements, and hence I am selecting two elements X and Y from the set Z. I am choosing two integers at a time. Now, let us start with the first pair and we shall prove whether this is there in the relation or not. Now, if X, Y belongs to the relation R, then if the pair is in the relation, then it should have to satisfy this condition. X minus Y is an integer, and this implies that X minus Y is an integer. We shall simplify this as writing it as X minus Y is equal to some integer P, where P is nothing but an element of integer. If I am subtracting any two integers, I am getting a number, and that number is an integer. Now, in order to prove that this is also in the relation R, I will take out minus common and we will be left with Y minus X is equal to P. And this implies that Y minus X is equal to minus P. You know that if the positive number is in the set Z, the negative number minus P is also in the set Z, and hence you can prove that Y, X also belong to the relation R, and hence conclude that R is symmetric relation. Finally, the last one, transitive relation. Remember the condition. if you are having two elements of the kind A, B and B, C in the relation R, then A, C should also be in the relation R. Now, we need three elements in order to prove the relation is a transitive relation. That is why I am taking X, Y, Z belongs to the set Z. Now, take two ordered pairs at once. I am starting with this condition, that is, if X, Y belongs to the relation R and Y, Z belongs to the relation R, then this implies that this should satisfy the given condition. X minus Y gives me an integer. Let me call that integer as P, and P belongs to the set Z, and Y, Z implies that Y minus Z should also give me another integer. Let us call it as some Q, where Q is also an element of the set Z. Now, we shall have a small simplification. I shall take this equation as equation number 1 and this as equation number 2. I shall make equation 1 plus equation 2. Adding up these two equations, we get X minus Y plus the second equation, Y minus Z is equal to the RHS P plus Q. Fine. Now, minus Y and plus Y gets cancelled and we will be left with X minus Z is equal to P plus Q. And you know that the sum of any two integers is always an integer, and hence P plus Q is also in the set Z, and therefore you can now conclude that X, Z is also in the relation R, since it is satisfying the given condition, and hence conclude that R is transitive relation. Observe that since the relation R is reflexive, symmetric and transitive, you can tell that the relation R is an equivalence relation. Check the next one. Show that the relation R in the set of real numbers defined by this, that is A is less than or equal to B, is reflexive, symmetric and transitive. Let us start generally again. Starting with the first one, that is the reflexive one. Now, if you are for the reflexive relation, you need to take one single element, and hence I shall choose one single element from the set R. I'm making it difference. This is the set of real numbers, and if I'm writing like this, this is the set relation. Okay. Now, if I'm taking any one element from the real number set, you already know that every element A will be less than or equal to the same element. Equal to is been satisfying there, and hence you can tell that A, belongs to the relation R, and hence conclude R is reflexive relation. Looking for the second one, that is for the symmetric relation. For the symmetric relation, we need two elements, and hence I am selecting two elements A, B from the set R. Now, if A, B belongs to the relation R, then it should satisfy this condition, that is elements should be less than or equal to B. Now, in order to prove it is symmetric or not symmetric, always check for the known results. Here, this is the known result. For all A will be always equal to A, that is a known result. But here, if A is less than or equal to B, let us consider any two numbers. If I am taking 1 and 3, okay, these elements are in the set of all real numbers, and if 1, 3 belongs to the relation R, that means that it is satisfying the condition. Yes, of course, 1 is less than or equal to 3, this is the right one. But if I am reciprocating that, that is 3 Is it less than or equal to 1? No, this is not less than or equal to 1, and hence you can conclude that 3, 1 is never in the relation R. This is called the counter example. If I am giving one single counter example, it is enough for us to disprove that the relation is not symmetric or it is symmetric. Now, therefore, you can conclude that B is not less than or equal to A, and hence you can conclude B comma A is not in the relation R, and hence R is not symmetric relation. Similarly, we shall now move for the third one, that is for the transitive relation. Again, for the transitive relation, we need 3 elements, and hence I am choosing A, B, C, which belongs to the set of all real numbers. Now, according to the transitive condition, if the element of kind A comma B belongs to the relation R and B comma C belongs to the relation R, it is a very well-known result that if A is less than or equal to B and B is less than or equal to C, then obviously A will be also less than or equal to C. You can check with a simple example. If I am taking 3 numbers 1, 2, 3, 1 is less than or equal to 2 and 2 is less than or equal to 3, and that implies that 1 is also less than or equal to 3. You need not write this example. It is enough if you are generalizing statement. Then this implies that A comma C also belongs to the relation R, and hence you can conclude that R is transitive relation. Look that the relation R is reflexive and transitive but not symmetric, and hence we can conclude that the relation R is not an equivalence relation. Check out for the next one. Show that the relation R in the set of all real numbers defined as A, B such that A is less than or equal to B square is neither reflexive nor symmetric nor transitive. Now again we shall start in the generalized way. The first one, the reflexive relation. For the reflexive relation, you need to select one single element. Okay, I am choosing one element A which belongs to the real number set. Now, whether A is less than or equal to A square for every element of the set real numbers, we shall now check out with a small example. Always while you are taking an example, choose for different numbers, like do not take always the positive numbers, choose a negative number and positive number, or a fraction or an irrational number also, because you are having the set of all real numbers. Now if I am choosing an element half which is in the set of real numbers, now let us check whether this element satisfies the given condition. Half and is less than or equal to half whole square. Half less than or equal to 1 by 4. Is this right statement? Not obviously, and hence half is never less than or equal to the quarter, and hence you can conclude that an element half comma half does not belong to the relation R. One counter example, yes, it is enough for us to disprove it, and therefore you can conclude that A is not less than or equal to A square, and therefore A comma A is not in the relation R, and hence R is not reflexive relation. Check for the second one, that is for the symmetric one. Recall again, for the symmetric relation, you need to select 2 elements at a time, and hence I am choosing 2 elements A comma B which belongs to the set of all real numbers R. Now, if we consider an element A comma B belongs to the relation R, if this kind of element is in the relation R, then it should satisfy the given condition, that is A should be less than or equal to B square. Now, according to the symmetric one, the reverse way, that is B less than or equal to A square. Is this true for any element in the set of real numbers? We need to again check. Take randomly any two numbers, because for the symmetric you are selecting two numbers at a time. If I am selecting 1, 2, which is in the set of all real numbers, now for the first case, that is 1 is less than or equal to 2 square, that is 1 is less than or equal to 4. Yes, this is the right statement. But if I am reversing 2 less than or equal to 1 square, is this the right one? 2 is never less than or equal to 1, right? And hence you can conclude 1, 2 belongs to the relation R, but 2, 1 is not in the relation R, and hence you can check that B is not less than or equal to A square, and hence B comma A does not belong to the relation R, and hence R is not symmetric. The last one, that is to check whether the relation is a transitive relation. Recall again, for a transitive relation we need to select 3 elements at a time, and hence I am choosing A, B, C from the set of all real numbers. And now, as per the condition of transitive, if A comma B is in the relation R and B comma C is in the relation R, then this should satisfy A should be less than or equal to B square and B should be less than or equal to C square. Then we should prove whether A is less than or equal to C square. For this, again we shall go for a counter example. If I am selecting randomly 3 elements from the set of real numbers, if I am selecting 2, -3, 1 from the set of all real numbers, you may observe that 2 is less than or equal to -3 the whole square, that is 2 is less than or equal to 9. Yes, the statement is right, and hence 2 comma -3 is in the relation R. Now, the second 2, that is -3 less than or equal to 1 square, -3 is less than or equal to 1. Again the statement is true, and hence -3 comma 1 also belongs to the relation R. Now, as per the transitive condition, if these two are in the relation R, then 2 and 1 should also belong to the relation R. If I am checking according to the condition, 2 less than or equal to 1 square is a wrong statement. 2 is not less than or equal to 1 square, and hence you can conclude that 2 comma 1 does not belong to the relation R, and hence you can tell A is not less than or equal to C square, and therefore A comma C is not in the relation R, and hence conclude that R is not transitive. Hence we have proved that the relation R is neither reflexive nor symmetric nor transitive. Try to solve these problems and you can send your answers in the comment section. Practice more problems of the same kind to become thorough with the concept of types of relations. That's all for the day. Enjoy doing math. Hope you enjoyed the video. Please don't forget to like, share and subscribe. Thank you.